All right, welcome back to another HPL seminar. I recognize a lot of faces in here, but there's many new faces, especially those undergraduates in 393, 395. So my name is Michael Bagley. I'm a postdoc with Walter Herzog, and this is Steph Ross. She's also a postdoc with Walter, and we're both going to be moderating the seminar series for this academic year. So every week, if you haven't been here before, we start at 3 p.m. The talks last anywhere from about 20 to 45 minutes. 45 minutes is on the very long end, hopefully more like 35 minutes. And then so we can have a nice long discussion, which just kind of, I guess, occurs or progresses organically until there's kind of some final ending point where it seems like people have all had their questions answered and everyone's pleased. So today we have a special seminar, which I think Steph and I are very excited about. I know Walter's very excited about it. So we have two of the undergraduate students who worked in Walter's lab this summer, Latif Omerkhil and Chris Tiessen. I'll start with Chris since he's going to go first for us. So we're going to do this a bit differently. Latif is going to give his presentation. Then we're going to do a question period for him. Then we're going to switch to Chris, and then we're going to do a question period for Chris. So rather than just bookending two things, because their talks are fairly different from each other, so this will help to make it a bit more, I think, cohesive between the talk and the question period. So, do you want to say anything? No. Oh, yes. 1 second, though. If you don't know, I'm going to plug this once again. Steph is the winner of the Banting Postdoctoral Fellowship, which is the most prestigious postdoctoral award. She's going to hate me really soon for repeating this all the time, but it's great. Okay, so with that said, I'm going to turn it over to Walter to speak to the 393, 395 students about how the class.
Now 396 actually. Oh. So it's not kinesiology 396. So my name is Walter Herzog. If you are a 396 student with the seminar class, then the way this works is that, first you listen to the seminar, you participate in discussion, and so on. When the seminar is officially closed, please don't run away, because then we stay back in this room, and about 5 minutes after the seminar has closed and is finished, we come back and then we discuss certain aspects of the seminar that I will explain to you in more detail. So listen carefully and don't run away after the seminar is done, because only half of your class is done after that. Great.
Thank you, Walter. Okay, so we'll move on and introduce Latif so he can tell us what he did all this last summer. So Latif is an undergraduate student who started his degree last fall, October 2022. So he's really kind of hit the ground running. His first semester or first summer of university, he worked in Walter Herzog's lab with, with Venus. I get confused with all the CP stuff. Anyway, so Latif worked all summer, and Latif won an award for the best poster presentation at, was it the McCaig Institute? At the McCaig Institute Summer Student Symposium. So very, very nice. And so this will be a really nice way to for him to show us what he spent all summer doing, working very hard. Latif is an undergraduate student in biology with a specialization in cellular, molecular, and microbial biology. I really liked his response to what scientific accomplishments are you most proud of, and he said that has yet to come, so he clearly wants to keep pushing forward. So that's very nice to hear. Aside from what he does, spending his time in the HPL, he loves to give back to the community, volunteering at homeless shelters, and then participating in various activities around the university. So without further ado, I'll turn it over to Latif so I can learn also what he did all summer. So thank you very much.
Thank you, Michael, for the introduction. Hello, everyone. So, what is cerebral palsy? Cerebral palsy is a motor impairment disorder found in children due to a static brain lesion. Now, it is characterized by loss of mobility and loss of balance. Now, both loss of mobility and loss of balance are said to arise from muscle weakness. So where does muscle weakness arise from in children with cerebral palsy? Now, among many other possibilities or reasons, the three major factors causing muscle weakness are decreased muscle volume, excess collagen in the extracellular matrix, and a reduction in the muscle's ability to produce active force at the cellular level. Now, the first two factors have been extensively studied already. What has not been studied is the third factor, or the muscle's inherent ability to produce active force at the cellular level. Now, before we move on, I want to remind you of how a muscle contracts to produce what we call active force. Now, a skeletal muscle consists of fascicles. And within these fascicles, you have the muscle fibers, which are essentially the cells of a muscle. And within these muscle fibers, you have your myofibrils, which are the contractile element of a muscle. And so within these myofibrils, you have a series of sarcomeres. Now, looking at this model, you might be asking yourself, well, how does this produce active force, or what active force is? Well, active force is just the force produced due to cross-bridge cycling. Now, this involves two contractile proteins. The first one is myosin, which we can see over here. And the second is actin, which we can see over here. Now, both the interaction of myosin and actin is said to be regulated by a protein called titin, which we can see over here. Now, looking at this model and what active force is and having this background knowledge, do you think that active force can be a contributing factor in causing muscle weakness in CP patients? Therefore, to investigate this, the purpose of my study was to gain an insight into the origin of muscle weakness by investigating both active force as well as sarcomeric protein contents. And what we hypothesized was that both active force as well as sarcomeric proteins will be reduced in patients with CP. Now, what did we do to test for this? We collected 11 adductor longus biopsy muscle samples from CP patients, and the ages ranged from 2 to 17 years old. Now, the GMFCS for these patients was 3 to 5. And what essentially this is, it stands for the gross motor function classification system. It's a system used to assess the severity of cerebral palsy. So a 1 is basically the patient is able to move with very limited amount of support, whereas a 5 is that they require a wheelchair at all times. And then this is just a figure showing a muscle sample from CP, which we have collected. And now, due to a lack of samples from typically developing children, this project actually instead utilized 2 gastric anemia samples from healthy adults. Now, once all these subjects and samples were collected, they were put into a skinning solution, which basically helped get rid of any or degrade any of the connective tissues to allow us to isolate single fibers. And then this is just muscle bundle under a microscope. Essentially, this is where we isolate the fibers from each muscle bundle. And now, once the fibers have been isolated, they get mounted on a force transducer and a length controller. So at the end of this process, we had a total of 38 cerebral palsy and 8 healthy adult muscle fibers, and they were used for active force, or to test for active force. Now, active force was measured at a sarcomere length of 2.4 micrometers. And once using the force transducer and the length controller, and once it was measured, it was converted to stress using the diameter of each muscle fiber. Now, what did we do to test for the sarcomeric proteins? Well, for the sarcomeric proteins, we ran a SDS polyacrylamide gel electrophoresis, which essentially just helped us separate the various sarcomeric proteins based on their molecular weight alone. And so what we used was a 10% SDS polyacrylamide gel for myosin and actin. So you can see the gel over here. And the top band is myosin, whereas the bottom band is actin. And we also used a 2.8% SDS page for titin. And we can see the gel over here and titin on the top. And so once we had these bands, what we did was we used MHJ to quantify the amount of sarcomeric proteins in each band. Now, having used these two protocols, what were our outcome measures and what were we able to obtain from these two protocols? The first one was the maximum active stress produced by each muscle fiber, so both for cerebral palsy as well as the healthy adults. And the second one was the myosin actin and titin content expressed as the CP to HA ratio. So that is cerebral palsy to healthy adults. Now, as for the exciting part, what were we able to find? Let's start with maximum active stress first. So here we plotted the maximum active stress of the muscle fibers for CP as well as healthy adults. And what we found is that there's actually a 46% decrease in the muscle fibers of cerebral palsy in comparison to healthy adults. And as for the sarcomeric proteins, let's start with myosin first. So here we plotted the ratio of CP to HA for myosin along the y-axis. And what we did was that we assigned 1 for the healthy adult myosin content, and everything for the CP is just a reference to the 1. So once again, 1 was used as a baseline. And what we saw is that myosin is not significantly different in CP patients in comparison to healthy adults. Now, as for actin and titin, we once again plotted the ratio of CP to HA along the y-axis, and what we found is that there's actually significantly less actin content in CP muscle samples in comparison to healthy adult muscle samples. And the same trend was actually seen with titin. So what we saw is that there's significantly less titin content in CP muscles in comparison to healthy adults. Now, up until now, I hope I have convinced you that there's a reduction in both active force as well as the 2 proteins responsible for producing active force, which are actin and titin. However, a question which arises from this is why? Why are we seeing decreased active force? Well, to understand why we're seeing decreased active force, I want us to revisit contraction at the level of myocardials once again. So this is just a 3D structure showing a myocardial. And then it also beautifully illustrates how a single actin can interact with multiple myosins synchronously and vice versa. So a cross-section for a healthy individual will look something like this, whereas a cross-section for a cerebral palsy would look something like this. Since our results suggested that there is significantly reduced actin and titin, here we can see that there's actually reduced actin content in titin on this cross-section. And so since we have reduced actin and titin, this could therefore lead to less myosin to actin interactions, causing the decreased active force which we're seeing. However, another question which arises from this is why only actin and titin are reduced, whereas myosin is staying relatively the same. Well, for that, further investigation is required to understanding why myosin does not change, whereas actin and titin are being reduced. However, from the results that we have obtained, we should promote CP patients to partake in resistance training, because resistance training has shown to increase muscle hypertrophy, as well as promote sarcomeric protein synthesis. And through this, we can actually preserve both active force as well as sarcomeric proteins in CP patients, therefore leading to less muscle weakness, which we are observing. Now, to conclude this project, I really hope I have convinced you that both active force and sarcomeric proteins are reduced in CP patients. And so a limitation of this study was that this project utilized healthy adult samples instead of typically developing children. And then lastly, I would like to thank Dr. Herzog, Dr. Venus, and everybody else that helped me with this project, as well as the other various people. Thank you.
Any questions?
That was great. Really good presentation, super clear, and just very well done. But you mentioned the limitation at the end, and I'm just curious if you can comment, if you know what the implication might have been with that adult sample as a control. Do you have any idea if it would have had an influence?
Well, based on literature and some of the work that's done in our lab, there shouldn't be a major difference between the active versus sarcomeric proteins. And so I just wanted to put it in there because it is a factor which could be causing like an error in our results, but it's not like a very big difference that we would see based off literature and the work that my lab has done.
Just one more quick one. There was that one outlier with the Titan group.
Yeah, I saw that too. That is an outlier. Most likely.
I mean, I know this is anecdotal, but does that have anything to do with their level of function? Because I know you had a range from 3 to 5. Is there anything that, like, the range of your cerebral palsy group was a 3 to a 5? I think you said.
GMS, yes.
Oh yeah,
Yeah. Yes. Right.
probably, but we're not very sure because probably, but I can't really comment on that because I don't know that much about it.
I got like 2 rapid fire ones and then like a more real question. But my first, probably very naive question is, how do you ensure that the sarcomere in the muscle fiber is at 2.4 microns?
We use laser diffraction.
Okay, so you're able to see the sarcomere.
So what we do, we shine light on it, and what we do, we get a certain pattern, and so once we see that pattern, we know that it's electrical.
Okay, and then the other question, sort of quick question, is you said that the gels were used to quantify the amount of protein in the muscle fiber, and so how do you ensure that you have a fixed volume of fiber? Because the cerebral palsy fibers are probably thinner in diameter and whatnot, and so I'm not really clear if that measurement is sort of counts for that, or
Yeah, so what we did is that we actually inserted 4,000 micrograms of proteins per milliliter in each well. So that just served as a control.
okay.
Yeah.
I'll
So there's a
trust.
certain amount that you put in each well.
Yeah, okay. All right. And then, and this is kind of a loaded question, but there's something behind it. Did you look at contraction velocity? So it would be interesting to look at this because this phenomenon, what you see, this decrease in thin filament density, is something that you see with disuse. This is what you see in bed rest studies, is what you see in spaceflight studies. You never see changes in myosin. You always see reductions in the thin filament density. You see reductions in the force production capabilities of the fibers, but actually it contracts much faster because people think there's just it's less for the myosin heads to pull against. It just happens much faster. But anyway, it just might be interesting. I don't know if you could look at something like contraction velocity.
Look into it. Yeah, we'll definitely look into it.
Thanks, great.
Can I make a quick comment to the space flight? You know, in bed rest and space flight and so, what typically happens is that you lose your slow twitch fibers first, and then you keep more of your fast twitch fibers. And so I don't know about the space flight and so exactly what they have done, but it could be that you just have actually a shift in the myosin heavy chain towards fast twitch. But that's an interesting point because I don't think anybody has ever looked at whether or not children with cerebral palsy have distinctly different fiber type distribution than typically developing children. That would be an interesting aspect to look at.
And this contraction velocity phenomenon, it's something you see at the muscle myofibril level. It's not something that you see with like isokinetic testing, or something like that. Of course, it's slower there. But yeah.
Yeah, so I'll definitely look into it. It seems interesting.
The reason why, well, in CP, it likely would be slower because what we also know, what we have found in a couple of studies on children is that their fascicle lengths are substantially shorter. So in the medial gastroc, in the study that we did with Sigrid and Matthias here a while back, we found that the fascicles are only about 60% of the length of a typically developing child. And then not only that, then the sarcomeres were overstretched. So you have less sarcomeres in series. And when you have less sarcomeres in series, since every sarcomere has a certain inherent velocity of shortening, so just because of that, you would get a reduced velocity on the muscle level. But maybe tries to compensate for that by remodeling and putting in some fast myosin heavy chains, and so that inherently gets faster. Of course, the muscle structure gets slower. That'd be interesting to look at.
Do you think, could the skinning process change anything between the two muscles? I assume that like CP muscle is more fibrotic, it's more kind of like connective tissue built in this, but you're kind of taking these differences away.
Yeah, but we're looking at the fiber, if we're looking at the level of our muscle, yeah, the connective tissue does make a really big difference. But if we're looking at a fiber level, it shouldn't make that much of a big difference because we have skinned them already and we're looking at a fiber. So I'm not sure, maybe it could, but maybe not.
Yeah.
Most likely not, because it is just a fiber.
So do you think that then that, like you take these your results at the fiber level and try to extrapolate them kind of to higher orders of organization? And so do you think then you might be underestimating the differences? Like you take these results and you go, okay, well we skin these things, but it won't go to the whole level. You have these structural differences. Are you underestimating the difference or overestimating?
Definitely are, because what previous studies on lecture we have looked at, they've looked at passive force. We're looking at active force, but they've looked at passive force. And what they see is that there's decrease in passive force at the fiber level, but when we go into the muscle level, there's actually decrease because of that collagen. Yeah, could be making like it could have an effect, but not a major effect.
Oh, yeah, thank you. Great presentation.
If you tested my fibers instead of the skin fibers, do you do or are you trying to purchase?
Yeah, because the skin process is just to create any of the excess connective tissues, right?
So like so you think the other cellular components that are present other than the myofibrils that are present in the skin fibers do not myofibrils, do you think that they're making a difference? And then do you think that, so you focus kind of like on the content and these studies also with the form. Do you think that's the only difference, like that is primarily what's explaining the differences, or do you think there's differences in like binding dynamics?
That's something that was very interested in, to see why, if I'm getting the question right, why like specifically actin integrin decrease. Like I was looking into that, but I don't have a clear answer for you there. Because it's interesting to know why only actin integrin decrease, whereas myosin is the same.
Do you think that, say, the titin that's still there is working functionally the same as a healthy child?
Further investigation will have to look into that.
Any questions?
Yeah, I had another question. Why did you do that? Why did you normalize, not normalize? Why did you take all the adult muscle data and just reduce it down to that value of 1? Do you have not a spread in the, is there a spread? What's the spread like in the adult data?
It's, so what we did, it's okay, so we had two samples, right? 2 up there and 2 down here. Took the average of both. That still has statistical difference, like there was a statistical difference.
Yeah.
But we would set it easier to put it this way. Like just making reference to it instead of just having to
Yeah, you know that the comment that you made at the end that maybe with strength training, you could kind of prevent that loss of certain, sarcomeric proteins, and we talked a bit about that already, and because these children very often they get a lot of physiotherapy and mobility and strength training, and so I wonder how realistic you actually think that might be, that with strength training you could improve that or even preserve it, as you mentioned, preserve that content of the proteins.
So yes, you're right. There's a lot of work being done with CP patients that are already encouraged to participate in resistance trainings, but it seems like it's not very effective. And so something that I would suggest them doing is using collagenase, because that has shown to reduce muscle stiffness and therefore can contribute to like less muscle weakness as well, because the motivation factors contributing to that.
Can you explain that? So you use collagenase, you get rid of fibrosis, so you have less passive stiffness. And why? How do you think that would improve active force?
That's not something like I'm really sure about, but I think if we just debate the speed contents, because if they're moving their muscles to produce force, right? It's like moving your arm in a clothes, like in water, like, you know what I mean? Like there's more resistance on it, so it's much harder to move it, right? And so if we have a contraction occurring, if there's more stiffness or more resistance on that contraction, right, that could be causing the muscle weakness.
Seems if there's more resistance, you would think there would be more force, you know?
Yeah.
But you know, I don't know the answer either. I just wanted to know, you know, what you think about it.
Just quickly to build off Walter's point, you know, I know in athlete populations, a lot of times eccentric training is thought to be give a different response with muscle compared to your typical resistance training. And just going back to that point that Walter was sort of raising about different types of exercise, have any studies that you're aware of or anything that you know of, has anyone looked at the role of stretch training, so eccentric training, on the muscles of children with PCD?
That's a really good point. So there's not many studies looking at specific, like they've extensively looked already at passive force and just passively everything involved in exercise issues, but they haven't specifically looked at like active force. Like there's essentially no papers that have looked at like scholarly papers that have looked at active force already. So there's not much out there to work with, if you know what I mean.
Just keep popping up in my head. Efficacy of exercise. So you say it's not effective. Has there ever been a case control study where you take CP kids, you don't allow them to exercise? This would probably be unethical. You don't allow them to exercise, and then you take another group and you do allow them to exercise, and then done the comparison. So maybe it's effective. Maybe it is effective. Maybe it's just not good enough. Right? Just something I thought of.
Yeah, it's not formulated on
I have a question regarding the neural transmitters. That is there any like investigation on this type of things at the early age of these like diseases? So is there anything wrong with them so that the muscle cannot be like exercised or trained well? So at the like older ages, it will lose this type of like proteins that you mentioned.
So you're saying it's been neural related, like
Yes.
related. Yeah.
Do,
So
do you
there's
do you know anything related to that? Or
something that I do know is that these patients, like there's continuous stimulation, so there's continuous use of acetylcholine, but their muscles are not responding to it, or they're over responding to it. As far as I know, in terms of neural.
So maybe just to add to that, you know, in spastic cerebral palsy, there seems to be an exaggerated muscle spindle response. So as soon as you stretch the muscles a little bit, the muscle spindles start to fire and then contract the muscle. And so one of the reasons why they tend to have these flexor contractions, the children with cerebral palsy, is because their muscles are immediately activated with the smallest movement. And that makes them not only stiff because they have a lot of extracellular matrix and fibrosis, but it also makes them stiff because they are activated so readily. In fact, doing strength training in children with cerebral palsy is very hard because if you ask them to do a movement, then everything starts contracting. And so there are distinct differences in the activation and the acetylcholine release in these muscles of in the spastic muscles.
So you mean that in their early ages, is it the same? Like, does it have anything to do with like passing the ages or not?
That seems to happen very early on. You know, I think you mentioned that the youngest children that we had here are 2 years old, and they already get. And the reason why they get samples is because they get operated. You can only get muscle samples from children that undergo scheduled surgery, because then the doctor literally cut the muscle, or in many cases, then the muscle becomes functionally useless for a while. So then they can easily take a little sample for us. And so some children are very, very young when they get this operation, because the brain lesion that induces that typically occurs at birth. And so then the situation evolves fairly quickly.
We'll wrap up here for So our next speaker is Chris Tiessen, and he's another summer student who's in the lab. So Chris started his undergraduate degree in 2021, and was also a summer student last summer in the Herzog group. And he's interested in all sorts of globulin mechanics. And he recently presented at the Biophysical Society in spring. And in his spare time, he builds model rockets.
Great. So just a quick outline. So I'm going to talk about two things today. First, I'm going to talk about immunoglobulin domain mechanics during stretch, so unfolding, and then immunoglobulin domain mechanics during relaxation. I'm going to talk about refolding. So yeah, this will all make sense as we go through it. So the first thing is that all of the work I've done has been at the level of the myofibril. And so I'm one level down from Latif. And so the reason why is because when I'm looking at immunoglobulin domain mechanics, those are in Titan, and it's very, very small. And so the smaller the preparation, the better the resolution we can get when we look at these systems. The other advantage is myofibrils don't have connective tissue, which means that what we're looking at is specifically muscle tissue. And so this is what these preparations look like. This is a myofibril. These dark bands are the myosin. You can see the Z disc very faintly there. And what I've looked at specifically is titin, which resides between the Z disc and the myosin. So it's very, very small. That little red rectangle represents pretty much the entire length of the protein that we're looking at, which, by the way, happens to be the biggest protein in your body. So although it's very small, it is very large on a protein scale. So what does titin look like? This is a half sarcomere, and so we have the Z disc on one side, and this is the M line in the middle on the other side. This is myosin here, and these are the actin thin filaments here. The protein that I've been working on specifically is titin, and this is a protein that attaches the Z disc to the myosin, and it stretches towards the end of the M line here, although the functional part of titin starts here and then goes to the Z disc. And there's three main segments of titin that are significant to mechanics. And those would be the proximal immunoglobulin domains, the PEVK segment, and the distal immunoglobulin domains. And you can think of the immunoglobulin domain sections as essentially a series of clasps. And these immunoglobulin domains, under sufficient force, can unfold. They can also refold. The PEVK, it doesn't actually unfold or refold in the same way, but it can extend and then shorten, and it requires force to do it. It's basically a giant spring with three segments. So let's talk about unfolding. So I want to walk you guys through the conventional understanding of passive elements in titin and what happens as we stretch a sarcomere. So the first thing that happens when we stretch a sarcomere, and all of my work has been done in rabbit psoas, so these length values are specific to rabbit psoas. They would vary subtly in other muscles like a mouse or something like that, but it's very similar in other muscles. So the first thing that happens when we stretch a muscle conventionally is that the immunoglobulin domains align. And so those immunoglobulin domains, the sections in between them are going to stretch out, but the immunoglobulin domains are still folded. They're not going to unfold yet. And during this process, we don't have any passive force on the muscle. Basically, we're just pulling the myofibril until it's like, okay, now it's time to generate passive force. The next thing that happens is the PEBK lengthens, and this happens between a sarcomere length of 2.7 and 3.6 microns per sarcomere, and that is this green segment here. And this lengthening conventionally accounts for pretty much all of the passive force generated by Titan in physiological muscle, according to the conventional understanding. So in physiological ranges, you wouldn't really ever get above 3 microns per sarcomere. And so most of what we can think of in terms of passive force in our muscle comes from PEBK. Although I'm going to challenge that a little bit throughout this talk. And then the last thing that happens is the immunoglobulin domains unfold. And we're pretty sure the proximal ones, we know they unfold. The distal ones, there's a little bit of a kind of a question mark. Do they unfold? Some people say they do, some people say they don't. But as we reach really long sarcomere lengths, so above 3.6 microns per sarcomere, we get immunoglobulin domain unfolding and those clasps come apart. What is important to note here is that the immunoglobulin domains are not the same. It's a series of similar arrangements in the protein, but they're not exactly the same. And so they have different stabilities, and certain ones unfold before others. But in general, these are the ones where we start to see unfolding of immunoglobulin domains. And so this basically forms our conventional understanding of passive force development in muscle. So it comes from this protein called Titin. What happens is first the immunoglobulin domains align, then the PEBK lengthens, and then the immunoglobulin domains unfold. And those 3 steps, they come from work done in isolated Titin molecules. They also come from work done on myofibrils. But a couple of things I'd like to say. The first is a lot of this work, especially with how long the PEBK is, relies on electron microscopy, which requires samples to be frozen. So it's not an in situ type of thing. They're frozen and then taken for electron microscopy. And then a lot of the work in myofibrils that has been done previously relies on modeling. So we're going to model the PEBK, and then based on our model, then we can figure out how long everything else is. And the trouble with that is that obviously now we are going to be affected by assumptions made by the modeling. So recently, there's been a couple of things that have challenged this conventional idea, and it's been called the molten state, just in reference to there might be an in-between state between a folded and an unfolded immunoglobulin domain. And so a couple of pieces of evidence here. The first thing came from single molecule experiments using atomic force microscopy and magnetic tweezers. And basically they showed that, look, if we take certain segments of immunoglobulin domains and we stretch them, they can actually unfold and refold at physiological forces. So I'm just going to talk about the unfolding first. So they can unfold around 6 to 8 piconewtons. These were forces that they found. There's also evidence for this in myofibrils using labels on the proximal IG domains. But a couple of questions. First thing, what about the distal immunoglobulin domains? How does the PEBK interact with this? And do molten state mechanics occur in myofibrils throughout the length of the immunoglobulin domain section? And so that's what I set out to test. And so this is how I did it. So the first thing is that we developed a labeling system for myofibrils. And so we got 2 antibody labels. The first binds to the N2A region, and the second binds at the distal PEBK. And you'll notice that these labels are very convenient because they divide up our 3 mechanical regions. And so now when I measure where these labels are, I can say, okay, this region is this long, this region is this long, and this region is this long. And so that allows me to say, okay, at any given point, how long are the proximal immunoglobulin domains, how long is the PBK, and how long are the distal immunoglobulin domains. It also allows us to take some really interesting photos of myofibrils. And so in this top left, there's a myofibril which has both of them illuminated, just to show you that they're both done at once. But then we have the F146 label here and the N2A label here. Now, just kind of a side note is that this has been done before, but we were able to do it without affecting the passive force generated by the myofibrils, which is somewhat of a big deal, because it means that we can actually use these results to infer what's going on in Titan without having to put an asterisk beside it and say, well, but we didn't get real passive force. So that's good. So what we did is we took isolated myofibrils and we did segmental elongation from 2.4 to 4.5 microns per sarcomere with a 0.2 microns per sarcomere stem. And so by the conventional model, we expect PBK is going to lengthen between 2.4 and 3.6. And then we're expecting the proximal immunoglobulin domain to lengthen after that. And we don't know what's going to happen to the distal IG domains. We'll find out. And so what did we find? The first thing is the PBK. And the PBK behaved exactly as expected. And this is good in terms of the credibility of the work we're doing, because there's been a lot of work in PBK elongation. It's quite well established what the PBK segment does. And so this graph on the y-axis is the length of the PBK, on the x-axis is the sarcomere length, and this is the contour length, which means that that is the length of the PBK segment when it is fully stretched out. So we should not really get any data higher than this. If we do, there's a problem. And this is exactly what we're seeing. We're seeing it's starting to stretch at around 2.7 microns per sarcomere. That's where passive force starts. And then as we stretch to around 3.6, we're reaching this maximum length. And so, this bodes well for the rest of the results. However, we found some really interesting results with the immunoglobulin domains. So in the proximal immunoglobulin domains, what we found is elongation occurs much earlier than we would have expected. So on the y-axis, we have the length of the proximal immunoglobulin domain segment, and on the x-axis, we have the length of the sarcomere. This is the contour length before unfolding. So any length we have above this length is theoretically, supposedly due to immunoglobulin domain unfolding. And what's interesting is that we see a pretty good trend, like R squared of like 8.4, which is very high for this type of thing. And we see unfolding happening relatively early, even at lengths like 3 to 3.5. And so this is an interesting result because this supports this idea that maybe these immunoglobulin domains can unfold at lower forces. And maybe we're seeing some more of this molten state behavior in the proximal immunoglobulin domains. In terms of the distal immunoglobulin domains, we actually saw almost exactly the same behavior as the proximal immunoglobulin domains. And so this is the contour length before unfolding. So anything above that we consider to be unfolding. And the same, we see this unfolding happening even down below 3 microns per sarcomere. And so this also supports this idea that we might be seeing molten state unfolding. So what can we take away from this? I think first off, it's fair to say that our labeled myofibrils support molten state immunoglobulin domain unfolding. And specifically, proximal immunoglobulin domain seems to occur at low lengths at similar forces. I didn't show the forces here, but they're very similar between that 6 to 8 piconewton threshold found in previous studies. And the similar behavior to the proximal immunoglobulin domains can be shown in the distal immunoglobulin domains, and the PBK segment shows basically exactly what we would expect according to the classic model. Okay, so let's move into refolding now. So just as immunoglobulin domains can unfold, they can also refold. And this refolding produces some really cool videos. So I'll have some videos to show you. So this is a myofibril. It has been stretched to 4.5 microns per sarcomere. In a couple of seconds, you're going to see we're going to shorten it. And you can see how it goes slack, and then it slowly recovers back to a top state. And so that recovery is due to immunoglobulin domains refolding. And so I'll just play it one more time because it's a nice video. Yeah. So a couple things to note with this video. The first is the time it takes for refolding to occur. So that myofibril is slack for approximately 8 to 10 seconds in this video. And so, okay, we think refolding is occurring somewhere in the range of 8 to 10 seconds. And it was experiments like these that started to help with our conventional understanding of immunoglobulin domain refolding, which is basically it occurs over a long time period at 0 force. So when you put a myofibril at 0 force, eventually all of the immunoglobulin domains are going to refold. And this is also supported by other data and just general experimentation. Whenever we do myofibril experiments, we wait approximately 10 minutes between doing one protocol versus another, because that's how long it takes for it to make a full recovery. So presumably something's going on during that 10 minutes, so we're probably seeing some refold. Then I did some experiments last summer that went like this. This is stretching to the exact same length, 4.5 microns per second. And then you're going to see me shorten over 2 seconds, and it's not going to go slack at all. It's completely taut during the entire time. And so I'll just play it one more time. So we thought immunoglobulin domain refolding was going to occur on the order of 8 to 10 seconds. Here, the shortening is happening in 2 seconds, and the refolding is keeping up with the shortening. So essentially, it's taut during the entire period. So the first thing you might think looking at this experiment is, okay, well, you're not at steady state here, because maybe your first experiment, you were at steady state, you stretched it, you held it for a super long time, lots of unfolding occurred, whereas this one, there really wasn't that much unfolding. So I did a series of experiments where we reached steady state. When you do that, you get a little bit of slack at the end of this 2 second period, but it's nothing like the other one. So refolding might be happening faster. So why does a myofibril remain taut? Basically, we have to attribute that to refolding because there's no other mechanism to recuperate length. So this informs kind of the molten state, but there's also been other work on the molten state. So the idea of the molten state when it comes to refolding is that actually we can see refolding observed in Titan at 1 and 3 piconewtons, according to that group, and we can see refolding between 6 to 8 piconewtons, according to that group. Now, the reason there's this range here is because IG domains have varying stabilities, and they were not testing an entire myofibril and an entire Titan. They were testing a segment. So it was like this segment of the proximal immunoglobulin or this segment of the proximal immunoglobulin domains, and they have varying stabilities. And so that's why they might see different forces. So the question is, how much work is contributed by this refolding if it's occurring? Like, is this actually a physiologically significant mechanism? So I don't know, I stretch my muscle passively. When I release it, is immunoglobulin domain refolding, recuperating energy? And secondly, at what force is this work contributing? So can this happen physiologically? And so how do we test this? I did 10 myofibrils through 6 shortening protocols. 3 of them were steady state prior to shortening, so three of those protocols each of those times, and the other 3 were non-steady state. And the idea with that is that maybe we can only access this molten state if we don't let it sit for a long time. So we can access this in-between state if it's just, just barely stretched that far, and then we bring it back. And so I used protocols that maintain force for the entire period to calculate this work. I haven't finished analyzing all of the data. I have analyzed specifically this and this, the 2 seconds of both, because those ones seem to be kind of the sweet spot where we see the myofibril remaining taut for the entire period, and the 10 seconds one take absolutely forever to analyze because it's a frame by frame analysis. Okay, so let's talk about what this data looks like. So the first thing that's interesting about this is, and I'll just go through this. So on the x-axis, we have the average sarcomere length. On the y-axis, we have stress. And this is a hysteresis curve, but I'll just explain it for people who haven't seen that before. So as we take the myofibril and we stretch it, we have increasing stress, so increasing force as we increase our sarcomere length. Then if I have a hold, some of the protocols that are steady state have a hold until we reach a steady state. Some of them don't have a hold because we're trying to access that hold state. And then after that hold, we have this recovery. And you'll notice that at the same sarcomere length, we're producing less force. That is supposedly due to immunoglobulin domains that have unfolded because now we have excess length, and so our spring isn't stretched as tight. So in order to figure out what refolding is occurring with this, it's somewhat difficult because refolding should be occurring during this shortening period. That's where we should get energy. And so what I did is I took our labeled data of how long the PPK was, because that data was quite reliable. I curve fit it, and then that was applied to the sarcomere length during refolding, because according to literature, the PPK should be responding almost instantaneously to changes in force in terms of its length. And so because of that, what we can basically say is the total amount of shortening is equal to the shortening by the PPK segment plus the shortening by immunoglobulin domains. And so with that, I can figure out how much shortening is coming from immunoglobulin domain refolding. And so we get a graph like this, which doesn't mean a whole lot. But basically on the left, we have normalized refolding events. And on the x-axis, we have the stress in the myofibril. So this is, you can think of this like a giant probability distribution that shows us the probability of a refolding event occurring at any given stress. And if I run statistics on this, we can find the average force during refolding is 6.8 piconewtons plus or minus 0.4 piconewtons in myofibrils. And so this is very, very similar to the 6 to 8 piconewton forces observed in the other paper. Now, when they looked at that, they specifically looked at an isolated portion of the proximal immunoglobulin domains, not the entire myofibril like I did. But it's promising that my forces are somewhat similar because immunoglobulin domain stabilities don't range that great. Like it shouldn't be like, I don't know, 10 times larger. So it should be pretty close. And the second thing is that refolding contributes 26 plus or minus 17. So, there's quite a bit of error in this data. I'm sure you can tell by the giant cloud. And that's just because we're limited by optical microscopy. And so that's why we have more of a cloud than a single trend, why I need so many data points to come up with the result of this. But refolding contributes 26% of the total work during the 2-second shortening period. So we can say approximately a quarter of the total work comes from immunoglobulin domain refolding as opposed to the conventional model where it pretty much all comes from PPK. So what can we conclude from this? So basically, I've shown support for molten state immunoglobulin domain behavior during both unfolding and refolding. So in unfolding specifically, proximal IG domain unfolding seems to occur at low lengths, and a similar behavior is apparent in the distal IG domains. And in terms of refolding, the average force during refolding is around 6.8 piconewtons, and about a quarter of the total work done during shortening comes from immunoglobulin domain. And with that, I'd like to thank everyone who helped me and the lab group, and thank you all for listening.
All right, who wants to start us off with questions? Okay. Perfect.
That was really interesting. And I know I've asked Walter this question almost every time that I see these presentations, and I'm always interested to understand how these sorts of things that you measure might contribute to, like what we say at human level, like stretch short cycle function, where you potentially have this contribution of energy from your stretch helping you with your shortening. And thinking back to the classes I've seen from Walter, where you think it's about like 4 to 6 piconewtons per cross bridge, or I think that's if I remember roughly. And I'm wondering the values that you pull out here. Can you speculate? Like, what do you think if you were to go from this level and you look at this stress strain relationship, what sort of contribution do you think that your values might have in a physiological organism?
Yeah, so, so the first thing is that the cross bridges being around 4 piconews, there's a whole lot more cross bridges than immunoglobulin domains unfold. And so during, at physiological lengths, if you believe my data instead of the conventional support, at a physiological length, we might have like 5 to 10 immunoglobulin domains unfolded. And so that's not very many compared to the number of cross bridges that we have. So the contribution is much lower than that. But what I can say is that if you were to flex your bicep and then have passive force in your tricep, and then during recovery, a certain amount would come from refolding. These results, and that 25% depends on how long you stretch it. So if you were to like super contract your bicep to 4 point, so your tricep was at 4.5 microns, 25% of it would be from refolding. But you probably don't do it that much. So let's say, I don't know, 10% or something like that might be from refolding of the passive energy. But that's only if you believe me that they're going to unfold at physiological lengths.
Maybe just a short thing to add here is that all these experiments were done passively, and there are theories out there, including the way we think about it, that maybe part of the proximal titin gets attached to actin, which then makes that free spring much shorter. And so we think that then actually during a physiological excursion, there might also be immunoglobulin domain unfolding and refolding. So we think that actively it might look quite a bit different than passively. That's something that Chris and Arnaud and other people will try to look at, just really the differences. And my hunch will be that it will look quite different when you do this active with the stretch opening cycle. And then I think we can answer your question better.
I have a question, Chris. I remember first learning about Titan, it was like, oh yeah, it's all responsible for eccentric force production. That's much higher than constant force production. Right? But your data here makes me think that the role is mostly just about maintaining stability in the sarcomere. So am I wrong? Has something changed in the theory of what like the role, specific role of Titan is? And then to build on that, like why build a spring with 3 distinct regions to it? Like what's the utility of having 3 different material properties versus one?
Yeah. So eccentric involves activation. And so the idea behind Titan contributing to that is the idea that Titan might bind to actin during eccentric stretch. And that would elongate a certain amount of Titan a bit more, producing the residual force enhancement. But all of this is passive. So this, we don't activate the muscle. There's no calcium in it. Like I'm flexing my bicep, not my tricep, type of thing. In terms of why having 3 springs, why having I'll just bring it back to the figure of that long ways. Okay, we can use this one. Why having this region, this region, and this region? Not exactly sure. A couple of theories that might. The first is that if we do have Titan binding, literature says that that's probably happening in the N2A region, which happens to be right between 2 regions. Potentially that could be significant, but I have no evidence for that. Second thing is that you can think of immunoglobulin domains maybe as an injury prevention mechanism. So let's say I overstretch my muscle, I still actually can stretch it more without breaking it. So they can unfold in that way. Whereas the PVK, that might be more of a physiological, it's supposed to stretch this way, but just in case it has to stretch this way, it has immunoglobulin.
Yeah, I guess that builds on another question. And you're like, okay, if you have the strength of your sarcomere is 4.5 micrometers, but that's like huge. It's crazy relative to like the normalized length. So like, yeah, that kind of gets, what is the probability that you would ever end up in a situation where you need this unfolding to occur, or it would, what's the likelihood that it actually occurs in a physiological scenario.
Yeah, so in a physiological scenario, you really don't ever get much above 3 microns per centimeter. But if you look at this data here, potentially we have a small amount of refold or of unfolding at 3. And if you look at this data here, potentially we also have a small amount of unfolding at 3. So perhaps something's going on. I would lean more towards if it's active and Titan binds to active, and some segments are overstretched, then that might implicate the immunoglobulin domains more. Because I think that this is a pretty weak argument for a lot of them, because this might just be noise, because just even the resolution of my microscope is like probably smaller than that difference.
Chris, can you quickly go back to your raw data, you know, the loop there?
Yeah.
That one, yeah. So my expression, I've got to go to the board here. So if I was Nicholas Kellermeyer, why do we have immunoglobulin domains and PDK? So Kellermeyer has argued in a 1997 Science article that it's the immunoglobulin domains get this very viscous behavior. You unfold the immunoglobulin domain, but then if you stretch or shorten, then mostly the PDK, which is essentially elastic. I mean, nothing's elastic, but it's essentially elastic. And so Tim Leonard and his other student tested that many years ago, published in a paper. So if you don't wait here, but you just shorten, so you are here and then you shorten right away, you get a very steep decline here. But if you don't go all the way down, if you just go a little bit down and go up again, it goes essentially up the same way. Virtually no hysteresis. And if you stretch it a little bit longer, and you do it, you get the same thing. You can go back and forth, and it's essentially elastic. So Kellermeyer argued you have the immunoglobulin domains and the PDK, a very viscous and a very elastic spring, so that you can have elastic behavior, very different sarcomere lengths after you have done unfolding of that right and on immunoglobulin. So that would be Kellermeyer's answer. Maybe, I'm not sure, but that might be it. There might be an
What's very
explanation.
appealing.
Yeah, I always thought that was really.
Any other outsteps?
You told me that you're really excited about doing this now. You have ideas filling out your head. So what are you most excited? Like if you were able to consider this art in the future, what would you be most excited?
So the next step is definitely to continue looking at this type of work, because this is pretty much undemonstrated in terms of immunoglobulin domain unfolding at low lengths. Like the literature is pretty consistent. It happens at 3.5, but I see it every single day I'm in the lab at like 3.2 when I shorten from 3.2. And so obviously there's some sort of disconnect there. The second thing, and this is just kind of something to mention, it's kind of interesting, is that when I stretch myofibrils to really long lengths, another thing happens that I haven't mentioned at all here, which is that Z discs start to expand. And we're not sure why that is happening. It shouldn't be happening, and we don't know how that works. And so that would be something else to look at.
Francie?
When you say the Z disks expand, could that affect your measurements? Because the Z disks are one of your boundaries for the proximal.
It could if that was how we were measuring it. But when we measure from the edge of the Z disc, not from the center of the Z disc. So because of that, we're not measuring the Z disc for this number. So.
And then for the distal, do you go to the M line, or like, do you take the center?
Yeah, I take the N line and then I subtract the length of myosin, which is highly conserved. So it's 800 nanometers for a half centimeter.
Do you think there might be a possibility to distinguish between a half unfolding, the multi-state, and the full unfolding? this type of an approach? I mean, you know, you mentioned that you think it might indicate, but is there a way to be sure about that?
Well, we would have to be able to measure whether or not an immunoglobulin domain was in an unfolded or partially unfolded state. And what's difficult with that is that we can only measure the length of the full segment. And if we consider, okay, we have 50 immunoglobulin domains in the proximal immunoglobulin domains, rabbit somas. And we say every time they unfold, they contribute. I think the difference between unfolding and folded is approximately 15 nanometers. And so we can figure out how many are unfolded based on that. If we say there's a halfway point in between, you can't solve that because it doesn't have a unique solution. So that's difficult to do in this type of work. So you might have to rely on a different approach, like a single molecule approach or something like that, where you can actually see the release in force as they unfold. I don't know, potentially. I'm not sure how you would do it.
No, I'm just wanted to see what idea you might have. I mean, it would be very, very difficult in a myofibrillary.
Theoretically, you could, if you were able to measure force exceedingly accurately, to an extent that we can't currently do, then theoretically you could pull on it just hard enough to cause molten state unfolding, but not too hard enough, or not too hard to cause fully unfolding. But we can't measure even close to that accurate forces right now.
The other thing, you know, was interesting when you answered the question about, you know, is this relevant? I guess Matt has left. Is this relevant unfolding, you know, relative to cross bridges and you know, Freund and Linke and Fernandez, and so they have argued in their work that yes, it is. And you know, because you said, well, it's probably a minor aspect in terms of work production, but you know how they argued that it might actually be fairly relevant and comparable to cross bridge work.
Yeah, I mean, the work that they found, the maximum was 3 times the work of a cross bridge with immunoglobulin domain people. And they argued that that's a significant contribution, but that also relies on that there are a lot unfolded.
Yeah.
And even their data on when they unfold shouldn't indicate that there's a ton of them unfolded at a physiological, like maybe a few.
But do you know how they got quite a bit of mechanical work from a single?
Yeah, it was magnetic tweezers.
Yeah, but I mean, why did they get a lot of work relative to a cross bridge when an immunoglobulin domain refolds? Because you said, you know, a cross bridge has 3 or 4 piconewtons. Yeah. An immunoglobulin domain has, you know, 6 piconewtons, let's say. So it has a little bit more force, but the other thing that comes into play is something else.
I'm not sure what you're referring to.
Yeah, it's the amount of shortening that you get.
Oh, in terms of the length, yeah.
Because when an immunoglobulin domain refolds, you know, it's about 25 nanometers, so it's 6 piconewtons times 25 nanometers, which then would be about 150 zeta newtons.
Yeah, their maximum
10
was
to the minus 21.
105 zeta joules.
Or zeta joules, exactly. Yeah, zeta joules, of course, has to be joules. Whereas, you know, 10 to the minus 21. Whereas for a cross bridge, you say, well, it's 3 or 4 times maybe 5 or 6 or maximally 10, absolute maximum 10 nanometers, which then would only be 30 or 40. So they get quite a bit of work, more work from a single immunoglobulin domain folding compared to a single cross bridge step. Yeah. And then you don't, you know, then you said, well, we have so many more cross bridges, but you have, you know, about 102 cross bridges per half myosin. You only have 6 titans. But even in a fully activated state, we think that any given instant time, there's only about 20 or 25% attached. So, you know, 100 divided by, you know, 25%, it's about 25 are attached. So if you have 25 attached that produce 30 to 40 zeta joules, and then you have 6 titans with multiple immunoglobulin domains,
Yeah.
then their argument is that actually the work contribution could be greater.
I would, yeah, that's interesting. I didn't multiply it out, but one thing I would say is that like physiological like ends here.
Yeah.
And the resolution of my system, my bands are approximately 150 to 200 nanometers. So that's like here to here. So this is within the noise of the system for us. And so, and also this amount of length between here and here, that's about 4 immunoglobulin domains. And so at the very maximum physiologically, maybe we have 4 unfolded.
Yeah.
So, yeah. But potentially that, could be done unfolded.
It'll be interesting to do that in the active one and see what happens there.
All right. Seems everything, so let's thank Chris again for this talk.